Okay, let's do an example here. Let's say we have four different plants, and each one has different production capacity. So the maximum number of units it can produce at any given time, as well as different fixed and variable costs. So we have four different plants here: A, B, C, and D. They have production capacities of 50, 250, 175, and 125 units. So that's like the size of each plant. Different fixed costs. So if you go A, B, C, D, you have fixed costs of $600, $700, $500, and $800. And then each one also has a different variable cost rate in terms of dollars. So the variable cost rate for plant A is $25 per unit. For plant B is $20 per unit. For plant C is $17 per unit. And for plant D is $30 per unit. So now the question is, what's the cheapest way to produce 100 units? So let's take a look at those numbers again and see if we can figure it out. So just by eyeballing it, what we see is that plant C is pretty clearly the cheapest way to produce these units. It has the lowest fixed cost, so $500 just to keep the lights on. And it has the lowest variable cost rate at $17 per unit. So if we could, we would want to meet this demand for 100 units using plant C alone. Now remember, we want to try to minimize the cost of meeting 100 units. And if you look at the production capacity of plant C, the question then is, can we do this? The answer is no. The most we can produce at plant C is 75 units. So it probably makes sense to produce 75 units at plant C and then 25 units somewhere else. And then our choices would be plant A, B, or D. And my guess is, just looking at it, that we would want to also produce 25 units to meet the demand of 100 at plant B, because it has a pretty low variable cost rate, even though its fixed cost rates are not the lowest. So let's take a look. So, yep, sure enough, the answer is that we want to produce 75 units at plant C and 25 units at plant B. So if we wanted to look at the total cost of meeting this demand for 100 units, we would add up the plant C costs first. So our fixed costs are $500. We have to pay that no matter how many we produce. So $500 plus 75 units, because we're going to maximize production at plant C. And 75 units are then multiplied times the variable cost rate of plant C, which is $17 per unit. So we also have to add that to the production cost from plant B. Plant B has a higher a fixed cost, so $700, and we're only going to produce, and we add to that its variable cost, we're only going to produce 25 units at plant B, but we have to multiply those times a slightly different variable cost rate, which is unique to plant B, which is $20 per unit. And if you add all of this up, you get a total cost of $2,975. Okay, so that was a really simple example for lots of reasons. Now let's think about a slightly more complicated situation. Let's say the variable cost rate. Remember last time we talked about those four different plants might have different variable costs, but the rates themselves were constant. So one plant might say the variable cost rate might be $20 per unit. For another plant, the variable cost rate might be $30 per unit. So what if the variable cost rate for individual plants is not that simple? What if it's not a constant, not a linear function? So if the variable costs are not a constant rate, in other words, they're nonlinear, then the total cost is not going to be a linear function either. And if we want to represent cost functions that are nonlinear, we might think about using a polynomial. And so I'm sure everybody's seen a polynomial before. The generic way of writing that here would be, total cost in dollars is equal to AX plus BX squared plus F. And X here is our decision variable about how many units to produce. A and B are constant coefficients. In other words, those are just numbers that are sort of given to us. and F would represent the fixed cost, because no matter what the value of X is on the right hand side of the equation, F would still be there, right? So the bare minimum, even if X is 0, that means the total cost, C, is just equal to F, the fixed cost, right? So this would be our equation for the total cost if we had variable cost rates that were not constant. Okay, so let's dive a little bit deeper into this. So let's say we have two different plants, and each one has a total cost function, C, that's equal to some sort of polynomial, right? So the variable cost rates for each plant are not constant, which means our total costs are not a linear function; they're polynomials. So we have plant 1. Total cost at plant 1, we're going to say that's C of X, and all that means is that our costs are some function of X, and X is the number of units that we're choosing to produce at plant 1. So total costs at plant 1 are equal to 20, that's our fixed cost for plant 1, plus 1.7 times X, again, X is the number of units we choose to produce at plant 1, plus 0.04 times X squared. At plant 2, our total cost is a function of Y. A Y is just another decision variable that represents the number of individual units we're going to produce at plant 2. So in this case, at plant 2, total costs are equal to 16, which is the fixed costs for plant 2, plus 1.8 times Y. Again, Y is the number of units we're producing at plant 2, plus 0.03 Y squared. So we want to minimize the cost of producing 260 units. The total demand for production of whatever it is we're producing at these two plants is 260 units. So if we're thinking about minimizing something or maximizing something, that means we're doing what's called optimization, right? We're trying to figure out the very best way to make a decision, in this case, about how many to produce at each individual plant. So our objective, our goal, is to minimize the cost of both cost functions, right? So it doesn't matter. We don't personally care whether the units are produced at plant 1 or plant 2. What we want to do is minimize the total cost of producing 260 units at both plants, right? So plant 1 might produce 0, and plant 2 might produce 260. And if that is what minimizes the total cost of getting to 260 units, then that's our optimal solution. So our objective, mathematically at least, is to minimize CX, which is the total cost of producing X units at plant 1, plus CY, which is the total cost of producing Y units at plant 2. Our constraint in this case, which means the rule that we have to follow in choosing values of X and Y here, is that we have to produce 260. So again, mathematically, we could say X plus Y, so the number of units we produce at plant 1 plus the number of units we produce at plant 2 have to equal 260. So there are lots of different ways you could solve this. A really easy one that I find kind of intuitive is that we could just graph it, right? So if we add CX plus CY, we can add those equations together, and we end up getting a function, right? And the function is 36, so that's the fixed cost for both power plants added together, plus 1.7x plus 0.40 x squared plus 1.8y plus 0.03 y squared. So that's our combined cost function for plant 1 and plant 2. And so what we can do is plug in different values of x and y. Now, the rule, of course, is that whatever pair of x and y values we choose, they have to equal 260, right? So if we choose x is equal to 0, y has to be 260. If x is equal to 1, that means y has to be equal to 259. And that's sort of expressed down here. We could express y and x in terms of each other. So y is equal to 260 minus whatever the value of x is. And so that's what I'm trying to express down here with that equation. Y is equal to 260 minus x. So what this figure, this graph shows is cost on the y-axis. So the total cost here is just the value of this equation that we have at the top, cx plus cy. And on the x-axis, what we're tracking is production at plant 1, which is the same as the value of x, right? So if we start all the way over to the left and we say x is equal to 0, that's the same thing as saying x is equal to 0 and y is equal to 260. And as we go from left to right on the x-axis and look at bigger values of x, each value that we choose corresponds to a different value of y, right? And then we can figure out for any given value of x what y has to be by plugging it into this equation. Y is equal to 260 minus x. So for each value of x and each value of y that we're looking at, we can plug it into this equation at the top and get a single dollar value, a single cost out of that equation. And that's what we can plot. So this blue bar shows the total cost of producing 260 units at different values of x and therefore different values of y too. And remember, we're trying to minimize the cost of doing so. And so if cost is on the y-axis here, what we really want to do is find the lowest point on this blue curve, and that value is the level of production at plant X that corresponds to the minimized costs. So if we do that, and you could use Excel to do this, we find that the total cost function is minimized when the x equals 112. In other words, when plant 1 is producing 112 units. What does that mean for plant 2? So remember, y is equal to 260 minus x. And so if we're producing 112 units at plant 1, that means we're producing 260 minus 112 units at plant 2, which is 148. So let's change our constraints just a little bit. Let's say that we know that x plus y has to equal 260, but we also are going to say that plant 1 has a maximum production capacity of 95. In other words, plant 1, and that therefore x, which is x is the number of units we're producing at plant 1, has to be less than or equal to 95. And the way we can visualize that constraint is this red line on this graph. So we can draw a red line right at 95. And because we're tracking x on the x-axis here, we know that the solution that minimizes the cost of producing 260 units while also adhering to this constraint that x has to be less than or equal to 95, our solution, whatever solution we pick, has to be to the left of that constraint. And so what's very clear at this point is that the solution here is just to produce 95 units at plant 1, or x equals 95, and then to produce the remainder at plant 2. So that is the solution. When we put in x is equal to 95, that minimizes the solution while also adhering to this additional constraint of a maximum production capacity at plant 1. So if we plug in x is equal to 95 into our equation down here, y is equal to 260 minus x, we get y is equal to 260 minus 95, and that gives us 165. So adhering to both constraints, the way to minimize costs here is to produce 95 units at plant 1 and 165 units at plant 2.